I'm Siddharth from Penn State, and today I'll be talking about constructing robust persistence diagrams for topological data analysis. This is based on joint work with Bharat Sriperambudur from Penn State, along with Kenji Fukumitsu and Satoshi Kuriki from the Institute of Statistical Mathematics. In the most general setup, suppose we're given a collection of points and our objective is to infer its shape. The shape of these points at some resolution is encoded in the collection of balls of radius epsilon centered at each of the sample points. As this resolution increases, new topological features are born or existing topological features die. By tracking the birth and death of these features, we get what is called a persistence diagram. Instead of looking at balls of increasing radii, we can alternatively construct a filter function on these sample points. In this setup, the shape is encoded in its superlevel sets. Here, as epsilon decreases, new topological features are born or existing topological features die. Tracking the birth and death gives rise to the persistence diagram from the superlevel filtration. A similar notion carries forward for sublevel filtrations. In the statistical setting, we assume that the sample points are observed from some probability distribution. As a result, the persistence diagram obtained from the empirical filter function is a random element in the space of persistence diagrams. Some common examples include the distance function, the distance to measure, and the kernel density estimator. The celebrated stability result guarantees that persistence diagrams are stable with respect to small perturbations of the sample points in the input space. However, if even a few outliers are added, then it can dramatically affect the topological inference. Our objective is to better understand the sensitivity and propose more robust alternatives. To this end, we consider the robust kernel density estimator, which is obtained as the solution of an M estimation problem in a reproducing kernel Hilbert space. In practice, this is nothing but a weighted kernel density estimator, which can be solved quite easily. The robust persistence diagram is obtained from the superlevel filtrations of the robust KDE. In robust statistics, influence functions are arguably the most popular tool for examining the sensitivity of an estimator. Unfortunately, the space of persistence diagrams is not directly amenable to classical sensitivity analysis. We generalize this notion using tools from metric geometry. We define the persistence influence as the influence outliers have on the resulting persistence diagrams in the bottleneck metric. We have some results on how robust persistence diagrams are for several filter functions. In a nutshell, the weight function associated with the robust KDE weighs down extreme outliers, and the resulting persistence diagram is far more stable. And this is what we observe in practice. As the outliers are made more extreme, there's little to no influence they have on the robust persistence diagram, while the persistence diagram from the KDE and the DTM have a noticeable impact from the outliers. Having established that the robust persistence diagrams are indeed more robust in practice, a natural question to ask is whether this comes at the price of statistical efficiency. We show that the robust persistence diagrams are consistent, and more importantly, if the kernel is sufficiently regular, then the robust persistence diagrams have optimal convergence rates. That's to say that we can get robustness for free without compromising on statistical efficiency. We also provide some methods for constructing uniform confidence spans. And that's it. And we have some code available on GitHub, along with some machine learning applications that show useful improvements. Thank you for your time, and we look forward to seeing you at the poster session.